got three metal bars lined up one above each other and a metal sphere on the end of a piece of string, and it's arranged so that this can swing in a larger circle and then a smaller circle. If the sphere is released from the right height, it can swing around like this and hit the metal bar in the middle. So from this height, it doesn't make it. From that height we get a resounding thud when it hits. The question is, what is the minimum height for which the sphere will hit the bar? I need to measure the distance between the two bars, which will be the radius of the smaller circle, and that comes to 21.5 centimetres. I also need to measure the height of the centre of the sphere above the table, which is approximately 11.5 centimetres. If the sphere just hits the bar, the string will be on the point of becoming slack. So the only force acting on the sphere will be its weight downwards. This will be the resultant force. So as we've got circular motion, mg, the resultant force, will be equal to the mass times the acceleration, which will be v squared over r. We can cancel the m's, we can rearrange to get v squared equals rg. I'm now going to use conservation of energy. This is the lowest point of the sphere's path. This is the lower bar, and this is the upper bar that the sphere we want to hit. This is the starting point of the sphere at a height h above this level of the lowest point of the sphere. When the sphere starts, it has no kinetic energy because it's released from rest. At this point, the kinetic energy of the sphere will be a half mv squared, and that will be equal to the potential energy that's lost. So we need to look at the change in height, which will be this distance here, which will be h minus 2r. So the potential energy lost will be mg h minus 2r. We can rearrange that to get v squared equals 2g h minus 2r. From our consideration of the sphere at its highest point, we had that v squared was equal to rg, and by consideration of energy we had that v squared was equal to 2g h minus 2r. Rearranging that, we can show that h equals 5r over 2. Now we can substitute our radius, so h will be equal to 5 times 21.5 over 2, which equals approximately 54 centimetres. Because I want to measure the height above the table, I will add on the 11.5 centimetres and obtain 65.5 centimetres for our release height. I will release the sphere from a height of 65.5 centimetres. It just misses the bar, so I'll release it from just a tiny bit higher, let's say 68 centimetres, and it hits nicely. The reason that we need to go a little higher than our prediction is that the sphere will be subject to air resistance as it moves, and some energy will be lost.